hold this system where we still have opportunities to share and to discuss vital issues regarding the industry, and not just basically the industry, but it gives us opportunity to interact, especially this period of COVID pandemic. Hopefully, when post-COVID, because we are not really in post-COVID presently, so really post-COVID, where we can have opportunity to have a physical interaction. I still hope that we will be streaming this kind of events, because they are well researched, well discussed prior to coming to the public. So, and I want everyone that will be attending this to know that the group, the study group, have done a lot to do it. They've done a lot of work behind the scene to ensure what is coming out is very, very quality. So, in the coming days, actually, we'll still be having a lot of programs. On Thursday, we're having a distinguished lecture on Thursday, same time, 5:30. I'm very sure, Simeon, you should put the link for those that have not registered to register. We'll be expecting as much people as possible. Network, send it to your friends, colleagues at work, and so on and so forth. It promises to be a very, very enlightening, distinguished lecture. So for this one we're having to the gas well de-liquification, I've had opportunity also of looking at the abstract and some of the discussions. So I'll be standing by also to see one or two things I can actually also benefit from this. So thank you again for the study group, for what you have done and what you are still doing. And I hope everyone will benefit immensely from this. So thank you very much without taking much of your time. Thank you. Over to you, second.
Yeah, thank you, session chair. So I'll check again if Dr. Eke has joined this call. So is Augustine not here? So similar, the latest slide was not shared with you, right? Hello, Simeon.
Section director, I feel that because we know this thing is partly presentation, which is like one. The presentation part is 1/3. 2/3 is basically discussion. So even without the latest slide, whatever slide you have, I think you can just go ahead. And it's a basic thing that you all know the subject very well. I think you should go ahead, and then so the others can now contribute. I think it's still okay.
Okay, so I'll have to then dig it out. But really, the plan wasn't that I'll present. This is like a stopgap, correct? Instead of giving people waiting, I just thought someone has to be saying something until we have full complement of Dr. Frank. I think maybe internet issues are affecting this.
That's correct. We've seen this in some of our programs. So I think I mentioned it to Dr. Kereke that we should have a backup. It happens. So we always have someone as a backup in case this happens. So this virtual thing, we have to keep several barriers in case one collapse, the other one. Yeah. It's a learning point for virtual.
Yeah, I think it's a valid learning point that we should carry for. And whenever everything, Simeon should actually have a copy of it. As
that is correct.
In a situation like this, you can. I was seeing a slide before. I thought it was
Simeon, I don't know if you copied
material,
that.
but we're
Simeon,
going to take this later.
Yes.
okay, please, for anyone at all, ensure you get the slide just before. And okay. Not only even getting it, you circulate on email few hours prior to all the people concerned.
Okay, I'm trying to get a version here to share in absence of nothing. Okay, so everyone will permit me. I'm just presenting a material I'm seeing for the first time here. So a lot of it will come for what I know already. May not be necessarily the text as it in this slide, but I'll try to be as consistent as possible. Okay, so I will share, and when you begin to see the shared material, tell me. Share. Okay. Okay, so I just share this. So let me know when you begin to see it. Are you seeing it yet?
Yes, we can see it. We can see it here.
Yes, we can see.
Okay, good. So I will just.
Erasmus, are you sure this is the updated slide?
Have you been in this meeting?
We have been looking for the updated slide. We can't find. So, in the absence of that, the section director wants to use the previous one he had. Or do you have it?
No, I don't really have it, but
Exactly. So I know Dr. Kerek is not. I think he has network issues. So basically, even the updated one, every one of you participated, so you know exactly where you need to comment to update it. So at least let's use what we have.
Okay, so I will just I'll carry on. Let me just see.
the one on display earlier seems to be the updated one. Don't you think so? Is it a different one?
Is this for me?
I mean, the one that was on display
No,
originally.
I don't know really.
That one looks like the updated one, not this one. This is a very old one.
Which one is that?
The one that was on display before you share this one.
That one is just agenda, right?
No. That one is just agenda.
Ah.
Yes.
I thought I saw slides, yeah.
Yeah, there was a slide, but it's agenda.
It's okay.
Okay, do you guys support? We just carry on with this, and maybe midway along the presentation, we'll now, if the latest version shows up, we'll just we'll take it on. Okay, so yeah, so is that carried? Otherwise, we wait for Dr. Kere. Let me even give a call again to see. Because I think he's going to do this far better than what I'm doing. I'm sending the presentation to Senior now. The entire session are waiting for you. Okay. We are waiting. Join the meeting now, at least. Okay. All
right. It looks like you said the presentation is with Simeon.
He said he's sending it to Simeon.
Yes, Simeon, can you check your email? He said he sent it to you.
It's not here yet.
Simeon, are you there?
He said he's sending it, but it's not here yet.
He actually said he's sending it, so he hasn't sent it yet.
Okay. Please,
So,
Simeon, be refreshing your, but let SD continue. Yeah.
Okay, I was saying since the material is coming, why don't we just give up? Okay, so I'll start with introduction and then we'll carry on with the right material. Okay, so this discussion is really around gas well de-liquification, and it's really around trying to address the issue of liquids building up in the well, starting from the sump or rat hole, all the way through the sand face, and then into the tubing and upwards, almost reaching to reasonable heights in the tubing. So the liquid itself is mainly water, both water of condensation from the gas or some water from the free water level, the reservoir that is mobile that could be accessing the pressure interval, or natural gas liquids, which we loosely call condensates. So these are the kind of liquids that we produce with gas. So over time, as the dynamics of the reservoir change, as the dynamics of the well change, it gets to a point where the gas, which is actually the transporting phase of the multi-phase mixture, begins to experience reduced velocity. And once that reduction in velocity starts occurring, what it means is that the carrying capacity of that gas reduces. And then you begin to see what looks like what is in the diagram here. Before, everything is flowing upwards, as you can see in the first picture. Second one, some of the liquid are not being carried along until the level of the liquid begins to build up more, until it gets to a point where the well is not able to carry on, because the back pressure on the formation now has exceeded the reservoir pressure, and the well dies. And now a lot of things happen after that. But it's important to know that it's very rare for this problem to start initially in the gas well. Usually with time, as the reservoir matures and some dynamics are taking place, including reduction in reservoir pressure, even formation damage and stuff like that can actually lead to this. So Dr. Keneke, is the material now with the latest slides? Hello.
He has sent it. I'm trying to download it now.
Okay. So SD, just continue doing your introductory part. If you are ready, let SD know so that I can switch over the slides.
Yeah, and then I hand over the presentation to Dr. Keneke. I'm actually struggling with code here. So, okay, so I mentioned earlier that the kind of liquid that causes this problem is water that accompany the gas production, which for some reason may condense out of the gas and begin to build up. But majorly the natural gas liquids, which are the heavier components of the flow stream, so they have a way of dropping out over time and then begin to cause this problem. So you can see that the profile of the well begins to show some erratic behavior. instead of being such a smooth decline for when the decline phase is off, because back then it goes up and down. Sometimes it now quits watering. So the source of the liquid, like I mentioned earlier, is it could be coming from casing or packer leaks, yeah, or maybe from what we call cooling, which is a phenomenon where you have an imbalance between gravity forces and viscous forces. Then you have a rise of liquid, as if the liquid is rising above gas because of the high draw that we expose the weld. And then when you also, for some reason, have a decline in the reservoir pressure, that also induces liquid. Anything that, if you picture a well, anything that can lead to a reduction in the flow rate of the gas well has a tendency of injecting liquid. Because gas being in the transporting phase must have sufficient velocity to leave the liquid along with it. Whenever that condition is not being met, the liquid will to try to become well. So yeah, so some preventive mechanisms for this phenomenon, in petroleum engineering, maybe in medicine, they say prevention is better than cure. But in petroleum engineering, it doesn't really hold. There's some prevention that means you shouldn't even produce the well after all. So sometimes we just let the problem occur and then we try to find a solution. That is what happens most times. You will not drill a well and say water will not break through ever. That means you will not produce at all. So some actions you can take to reduce or prevent liquid loading. It's as much as possible to ensure that you are producing this well at a high velocity. That is when you still have control on that. The interesting thing about that segment is, yes, that's the only way you can. When the energy of the well, if you like, still allows you to be able to throttle it as you wish. But over time, when a lot of decline pressure has happened, or then you can do pumping. A pump is for liquid, like install a pump, that pumps it out for you. Or even do gas lifting of gas wells. Yeah, but I hope you know in Nigeria are so blessed really requiring pumping. The kind of gas well inflation we do really is the kind of gas is we'll get to that. So foam, you can also inject foam of reducing the hydrostatic pressure of liquid. Getting a foam in there means the pressure that the liquid column is exerting on formation reduces when it's able to keep packing. But again, injecting foam continuously means major modification in the production system. And also be aware of fouling the process. And so okay, this is handling the liquid itself. So let me pause again to check. Simeon, are you ready with the new material now?
Yes, I'm ready. So you just stop sharing your screen.
Stop sharing. Yeah. Stop sharing. Is it a good time to take over? Hello, Dr. Koleke. Hello? Is anyone hearing me?
I can hear you
Yes,
now.
I can hear you also.
I can hear you now.
Okay. I don't know whether the responded.
Yeah.
Okay. So, Doc, if you don't mind now, it's time to carry on. Unless one needs, if you get to the point where I'm coming and then coming, right? Is it a good time? You can continue from where I stopped, so we do not go through what I've said.
Oh, okay.
Okay.
Thank you very much, and thank you. Good evening, everyone. Good evening, everyone.
Yeah, sure.
Good evening, Doc.
Can we roll the slides down to just after causes of liquid loading? Let's keep going down, please. Can we keep going down, please? Let's go. Let's go down more. Let's go down. 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 No. Can we go back a bit? Back a bit. Sorry. Back a bit more. Back a bit more. Back a bit more. Oh, okay. Let's move forward rather. Oh, that I think we've not gotten to where I'm looking at. Let's move forward a bit more. Okay, we can stop at symptoms. Yeah. So basically, yes, we can. Yes, thank you. So some of the common symptoms of liquid loading, like we know, liquid loading is basically a situation where we have the liquid phase composition of a multi-phase stream from the gas wells. They begin to drop off or drop back into the well bore, because basically the superficial velocity of the gas core, especially, that is supposed to drag this liquid film. The liquid phase often occurs in the form of liquid films that we experience at the walls of our tubings of our well system. So when our gas velocity begins to drop off, we get to a point where the gas core is no longer able to drag this liquid film up. And so that's when we begin to have liquid loading. And this often occurs when the reservoir pressure is low. So some of the common symptoms of liquid loading include common symptoms of liquid loading, things we observe and know that liquid load is around the corner, include the presence of orifice pressure spikes. We begin to have pressure spikes within our orifice. That's a pointer that we are about to experience liquid loading. Then another thing is erratic production and increase in the decline rates of our gas wells. We begin to have them drop off in our million scarf that we expect. For instance, we're expecting 50 million scarf or 10 million scarf, for instance. We begin to see a drop to 8 to 6 million scarf, and that's not what any operator wants. So again, another pointer is tubing pressure decrease as the casing pressure increases. So this is also another pointer to liquid loading in gas wells. Then another symptom is that the pressure survey shows a sharp, distinct change in pressure gradient. So we need to have a sharp, maybe our pressure gradient, for instance, I'm just making an instance, maybe it's at say 200 psi, something like that. Then we begin to have a sharp drop, which is not uniform as it were. That's also a pointer to liquid loading. Then annular heading. Annular heading is more or less some form of slugging. within the gas well system. So Simeon, can we move on to the next slide, please? So as part of the identification of liquid loading, we need to be conscious of knowing when we have onset of liquid slugs within the gas well streams. And liquid slugs mainly is, you begin to have fluctuation of those your liquid films. They begin to go up and down, creating oscillation within the system. So that's also a pointer to liquid loading. Then we begin to have increasing in difference between the tubing and casing pressure with time, similar to some of the things I mentioned earlier. Then sharp changes in the gradient, which is also similar to some of the points earlier. Then fluctuation in gas production. So these are very threatening symbols, which is not good. Then can we move on to the next slide? Thank you. So the causes or the major factors that contribute to liquid loading in gas well is when you have a drop in pressure drop, which could be from the fact that you're producing that gas well for a while and your reservoir pressure within the well begins to drop. Then high drawdown we are not able to increase. We are not able to get our gas stream come off very well. Then we could also have high wellhead pressure. These are all causes and consequences of liquid loading. Then high condensate gas ratio is also another key cause. Then we could also have leaks within our stream. Then the consequences or the results that will come as a result of liquid loading include we could have low productivity, which operator wants to have that. We could have low productivity. We could have intermittent shortings. We could have high operating costs, which these are the things that operators do not want at all. So, but these are the consequences and things that could result from liquid loading. And then, of course, most importantly, we could have an early abandonment, which is not what we want. Thank you, Simon. Then another important thing is what are the preventive mechanisms? Preventive mechanisms for liquid loading. So as liquids accumulate, we have increase in our flowing wellbore pressure. And there are several actions that we could take to prevent that. So number one is float a well at high velocity to stay in the midst of a flow, by the use of smaller tubing or creating lower wellhead pressure. So basically, you're trying to reduce the drawdown or to reduce any form of inhibition to having your gas stream or coming to the surface. Then another important thing, preventive mechanism that we can apply is the use of pump or gas lift. So be able to support the production of the gas phase up. Then we could also apply foam within the liquid phase. This could enable the gas lift the liquids to the well. And I would like to emphasize here, I was privileged to attend a training in the Netherlands sometime in 2013 thereabout. And this foam technique is one key technique that TNO, one of the major research institutes in Netherlands, are currently trying. And I think it's with the results from they've gotten, I think it's an area that operators, even within Niger Delta, need to consider very critically, because they had some foams that they could add within the stream that could enable the liquid phase droplet to kind of coalesce together and make it easy for the gas to push it upwards. Another technique is injecting water into the underlying disposal zone. All these are to enhance the pressure within the reservoir and help you produce the gas at a good pressure. Then prevent liquid formation or production into the well. So can we move to the next slide, please? So methods available in the industry to manage liquid loading include maintenance of the natural flow, assisted lift of the plunger, assisted lift of plunger lift, the downhole pumps, having downhole pumps within those gas wells to support the pressure within the system and make sure that you are able to overcome the hydrostatic head that could prevent your gas stream from coming to the surface. Then we also have downhole water sinks or downhole gas water separators. So because if we're able to separate within the downhole, what we need to lift from our gas well or up our gas well will be lighter and easier to lift. So next slide, please. So the next slide is about current and emerging techniques for de-liquification of gas wells. It's also key. We need to consider some of the methods we need to consider include sizing production strings or installation of a velocity string. So there needs to be properly designed strings which you could install, and as well installing them with injecting foamers, which I mentioned earlier, is one key technique that operators need to look out for because of its effect to cause a coalescing of the liquid droplets within the walls and make it a bit easy for the gas within the core to push the liquid up. Then compression is also another technique that should be given attention, and then plunger lift. And then we have in Fig A and B some of these methods illustrated. So can we go to the next slide? So still on the earlier slide was more around the current techniques. For some of the emerging techniques, we have the beam pumping. In the beam pumping system, it functions when the wells do not have enough pressure and gas liquid ratio is not conducive. So you use the beam pumping. So it's similar to using some form of downhole pump to manage your system. Then we also have hydraulic pumping, which is using hydraulically powered pumps to support your system. And then we have injection systems. Injection system, instead of producing water from gas, instead of producing water from the gas well, it's possible to rather inject the water into the zone below the gas, and this could enhance your production and prevent liquid loading. So some other future methods include automated intermittent production using wellhead temperature as a proxy to help in guiding you. Then you also have enhanced oil recovery method, which you could use as well, and then water lift downhole pump method as well. So can we move to the next slide? So nature and causes of liquid loading. Erasmus, I don't know if you can come in here a bit. Are you there? So, but I'll carry on. So, nature and causes of liquid loading.
Okay, I don't know.
Are you there? Yeah. Can you come in from this area, or do I carry on?
Yeah, so I think you have momentum already, but let me just talk through this then. Okay, so like Doc has been saying, it's really about low rates, right? So when you can, always ensure that the gas has a sufficient rate. And when I say rate has a direct proportionality to velocity, right? So just the fact that the nature of this is that low gas rates begins to occur, either the one you instigated yourself by producing at abnormally low chokes, or the one that is forced on you by dynamics of the rates of water. Like imagine cutting water, which means your envelope of man deteriorates, and the well is able to deliver is lower. Therefore, the velocity of the gas is lower. And then this is important to know that this is a transient phenomenon, right? And for you to really model transient phenomenon appropriately, it requires a lot of physics, right? And a lot of tools we use are steady-state tools like Postman that people use in modeling. So anything a steady-state tool can give you is only an approximation of this transient phenomenon, just like you know that. So it's transient, and because if you leave it after 4 hours and go back, the condition of the well has changed, the FTHB has changed. So it's just important to know, and the nature of this is that it's a transient phenomenon. So the height of liquids continues to build until eventually it kills the well. And then what engineers do is actually to identify and try to correct this. So you flog the well as quickly as possible. So it's such an interesting phenomenon that for normal oil wells, the tendency is to choke back when water is coming. But for gas, it is the opposite. The tendency is to open up the choke as long as you're able to. Because being able to open the choke is to ensure the well is being produced in the liquid envelope. And then field experience from engineers too. Some people try to design this out, but I tell you, in design, you are as good as the assumption you have made for the future state of that well. And what I mean by that is, somebody says, do a life cycle design. Then you do early life, you do midlife, and you do late life. Maybe early life, you have an idea of what it is, because you know the current is about pressure, the current, everything. But you can't even know, it's difficult to predict exactly what it will be in 5-10 years' time. And then the abandonment condition, maybe at the tail end of production of that is what it's going to be. So that's why there's no way you can do a design and it's perfect. And that's also why we have liquid loading because. So what we have here is a typical cycle. The diagram under that has 1, 2, 3, 4, 5. A typical cycle of liquid loading. Initially, you have high gas flow velocity. And then due to some factor, which I said, one way could be from you, the engineer, for some reason, the gas nomination, I mean, what the customers want you to produce, is making you to choke back the gas well. And then you begin to notice the buildup of liquid in the well. And then it gets to 3 where you now have a significant buildup of liquid there. And then there's actually a phenomenon that is very common in Holland. I don't know about here really, but where kind of osmosis happens and the standing liquid column in the well somehow disperses back into the reservoir. Because for liquid to stand on top of gas, it is not stable. In the end, when everything goes quiet, the liquid that's standing under gas will try to go under it again. So you notice that on number 4, the liquid finds its way back to the reservoir, and then you're back to what resembles number 1, and this cycle continues. So for you, you're not okay with 2 to 4, and that's what you're trying to avoid. If you can prevent this from occurring. If it does occur, we want to get back quickly to number 1 or a semblance of it, or number 5. Yeah. Okay, so yeah. Next slide, please. Next slide. Okay, great. So the causes are already, and nature of this presentation, I don't need to repeat what we said before. Pressure depletion. And just imagine anything like an influence the production rate of a gas well. Depletion is not pressure. Natural water encroachment. Water is never used for reproduction. Never. Just water and sand, not useful for anything. We have better water here to use. And then, if your production to be for some reason, you overestimated the capacity of the reservoir, and then you oversize it to be, then expect it will look very, very high. And then if you have formation impairment, it will cause deterioration of your inflow performance. And that also influences liquid load. Let's go to the next one. I think these are the 2 that I'll be focusing on. Let me see the next one first. Okay, I think I treated a case. Yeah. Next slide. Okay, so we just brought out a case in the Niger Delta because it's important we do not address this as a theoretical problem. It's ready to be aware and say, yeah, there's something called a liquid loading, but never see it. So this is a well that is completed with 7-inch tubing. So this is a well that is completed with 7-inch tubing, was a high-rate gas well, shooting over 100 million scf per day for over 5 years before we began to see decline. Yeah, so the initial CGR was decent, around 80, and of course it produced significant quantities of NGL. And then the aquifer support was moderate. What that moderate aquifer support meant was we're having some depletion, and about 8% depletion is not pressure, as occurred over time. And then the plant inlet pressure, this is very key. Every gas plant for processing or produced gas has a minimum pressure it is set at. That means everywhere you have to overcome that pressure for them to come into the gas plant. So the plant inlet pressure is 1,200. That means if a well has a floating air pressure of 1,000, that means the well cannot produce. You need to close it in because it cannot overcome the back pressure without required to enter the gas plant. And that is the basis for the theory of compression as a way of solving gas well liquid loaded. So I'll get to that. Okay, so increasing water cut actually is what led to. And then when the analysis was done, we saw that the gas water contact has invaded the lower side of the producing zone. And now, so there was a review of several solutions that can be put up for this. But in the end, because of how the kind of high capacity of the reservoir, what needed to be addressed is that inability of this well to meet the plant inlet pressure, which means if you bring another compressor in parallel just before the major gas plant to take the low pressure here and compress it to the plant inlet, this well will come back to production. And that was carried out, and that brought this well back to production. But what it meant was we did not address the water at all, or rather, the field that has this never addressed the water at all, but you were just flowing in with the water and then teaching the water in the plant. But the important thing is the compressor enabled the field operations to jack up the pressure from what the well is able to bring in at suction, and then discharge it at what is required to enter the originally existing plant. And by so doing, this well was taken out of a well that was in production. Next slide, please. Okay, so just to further illustrate that impact of compression, so I had to make a cartoon like this as an illustration. So every well, for that well to be alive, I think it's probably obvious that the well is able to flow all the way into the gas plant. So this is the kind of flowing to be air pressure over time, especially as some depletion is taking place and some water incursion is coming to the production. It kept depleted. Of course, sometimes you need to shut down and come back to production. These two troughs you have there. But then this FTHB continued to go down until it was not able to meet the plant inlet. What it means for such a well, just in case you see them, is you go there, there's fluid air pressure. But the problem is, it is not, sorry, when you close the you have fluid air pressure. But when you open it up, the pressure, and then it means the well will not be a useful asset to you. So, but if you justify a compressor and design it in a way that the suction end of it will take the low pressure from this well and then raise it higher enough for the plant inlet, you have restored the well to plant. So that's the reason I just said, let me put this for that illustration here. I think that's where I'll keep it long. Carry on, please. Thank you.
Okay, thank you very much, Eras. So can we proceed? So here we focus basically on the sequence and process of liquid loading. Because we've touched a bit on process of liquid loading because of the other sections that Eras has taken, I won't dwell too much on the process, but the sequence, I'll touch on that a bit. So almost all gas wells produce wet gas, so it's important that we know that there's always some portion of liquid that comes with the gas we are producing. And that's what often leads to the liquid loading in gas wells. So water and hydrocarbon condensate that's mainly the liquid phase composition. So initially, as my colleague Ras mentioned, we have high rates, and those high rates makes it stable for you to continue producing. But this is prevalent within annular flow regime when you have gas at the core, and then you're able to drag the liquid films on the side. If we look at the tubing we have on the right, figure 6, you see, some bubbles of gas, but within the wall, that's where you always have the liquid film. So until your gas core is flowing at a high enough velocity, that's when you can move those liquid films out easily. But once that gas velocity begins to drop, you begin to have problem as the liquid begins to soak backwards or begin to drag backwards and could load and then subsequently kill the well. And then this occurs mainly at the late stage. Liquid loading occurs mainly at the late stage of production with lower reservoir pressure, lower gas flow velocity, as it were, typically high liquid to gas ratio, where the liquid portion becomes typically higher than the gas phase. Possible water influx encroaching from the aquifer. These are all danger signs and sequence that could lead to liquid loading. And then you have more liquids and less gas, like I mentioned. Next slide, please. So here we try to illustrate a typical production scenario. where you have liquid loading. We can see the green portion, the green spikes. The green spike is the gas rate. Then we have the blue spikes, that's the liquid rate. And the red dots represents a typical forecasted production. So within the unloading region, which is the first region, we at all the way we want it, with gas moving at almost the rate that was predicted. And we also have, as we continue into the loading region, we begin to have liquid rates begin to increase. And we have a situation where our gas rate begins to drop. And that's why goes down, and then in region where you have a lot of noise fluctuation between the gas and the liquid phase, and that leads to the problem of the loading of liquid, which we don't want, and oftentimes this could lead to a killing of the well. So next slide, please. So here, this is pretty much similar to what my colleague Eras illustrated, so I won't spend too much time on it. We have the phase 1 at relatively good gas velocity, and the phase 2 where things are also relatively stable, but 3, 4 begin to have a drop in gas velocity. So, but it's important to note that in terms of flow regime, we begin to have liquid loading more of when we have slugging flow regime, where we have our gas velocity drop very well, because slugging is associated with low reservoir pressure, low gas velocity. And so that's where liquid loading is prevalent. But under annular flow, which in terms of designing, this should be what the design engineers should look at, how they could design maybe the production rates that they are looking at having within the course of the life of the field to occur mainly within annular regime, because from this study, a number of published works suggest that the annular regime is where you can hardly have liquid loading. So it's important to make a note of this, that the annular flow regime is key to kind of managing liquid loading. So can we move to the next slide, please? So the consequence, by way of summary, in terms of sequence, we have both gas and liquid being produced to the surface at ab initio at relatively good gas velocity. Then we have a decrease in velocity of gas over time, leading to possible reversal and accumulation of liquid bottom hole. Then 3, we begin to have, due to this liquid accumulation, the bottom hole pressure increases, and that's not where you want to be when you're delegated to manage any gas well. Then 4, we begin to have the liquid build up bottom hole, and then they begin to get re-injected into the formation, and of course that will lead to a lot of increase in pressure, making the hydrostatic head that you need to overcome to get your gas stream to the surface much more cumbersome to overcome. So this is pretty much the sequence you have. And then 5, you have near wellbore pressure recharging because of this fluctuation. So next slide. So in terms of process, clearly liquid loading is transient in nature. It's not a steady state thing, not a steady state phenomenon. It's a transient phenomenon where as a result of fluctuation or variation in the gas phase velocity, we begin to have a point where the gas velocity is high enough to keep us producing the gas stream. Then over time it drops, and that leads us into the problem of possibility of having these segregated liquid films dropping back and accumulating into a heavy density or heavy weight that gets back into the wellbore. Then another thing we need to take note of is an understanding of the flow features taking place within the wells. It's also important and how we can be able to predict, especially the regimes that we could experience, and then how understanding how we could also influence these flow regimes that we could potentially experience from that gas well to possibly occur within the annular flow regime. Then temperature, pressure, liquid hold up, these are some of the parameters around the bottom hole that we need to place our focus on. And I think, although it's pretty challenging to have that, but I think it's something that industry stakeholders need to start looking at, possibility of having sensors that could read off some of these parameters within the downhole region, because that is a potential way to be able to solve this problem much better. Next slide. So here, the focus is on exploring what happens post-annular regime, because annular flow regime is where you find it difficult to experience liquid loading. But post that, especially if you go into your slugging phase as your gas velocity drops, that's where the challenge is, and that's what we are looking at here. So annular flow regime is generally encountered in the early life of a vertical gas well prior to onset of liquid loading. So how to maintain this phase long enough should be at the top of the mind of any production team that is working on gas wells. Then in this flow regime, the liquid, water, and condensate flows in two different fields. You have the droplets and in the gas core, and then along the pipe wall, you have liquid films. Just like you will see, you have the palish blue part on the wall of figure 9. That's pretty much liquid film. This could, as your gas velocity within your gas core with the arrow downwards in the center begins to drop, these are potential problems that could happen. So the liquid film, rough liquid layer adjacent the wall, how can this be coalesced, maybe by way of foam and all that? It's important to understand how that could be done efficiently to help you manage in pushing the gas stream up. Next slide. And it's important to know that the waves that you experience, can we go back again? Simeon, sorry. The waves, these fractures that you experience here and the fluctuation is caused as well by the fluctuation in the gas velocity within the gas core. So next slide. So here we look at the physics of liquid loading. So basically you're looking at how you can transport the liquid films around your wall more effectively. So you have droplets, the gas core, you have the films along the tubing wall. How can you operate in a suitable gas velocity that can help you move this liquid film upwards? Then we need to make note of vertical flow. We need to be mindful of variation in droplet size. We need to be mindful of the film, being able to get the liquid film to move evenly, because if they don't move evenly, they could affect the gas velocity. They could lead to a drop in the gas velocity the more. Then another important thing to make note of is deviated flow, when we could experience this when the liquid film is also not evenly distributed. Then we need to be also conscious of the mass fraction of the gas that is the mass fraction contained rather in the droplets, how they vary. If they vary in an unsequential way, it could lead to this gas core not being able to push the liquid film more effectively. And finally, we have the liquid velocity. The liquid velocity is determined mainly by the gas-liquid, the share between the gas-liquid phase. So if that share is that share is like some form of friction. If that share is if it's high, we will expect that our liquid could coalesce better and could potentially drop more and within our wellbore. And this aspect as well is also complex in modeling, both using CFD or using simulation tools. So this is one aspect that further studies need to be employed to look at how to improve on modeling of this gas liquid phase share. Next slide, please. So here we begin to look at the areas that we can improve for us to be able to manage effectively an already loaded gas well to prevent stopping production. So managing loaded gas well focuses mainly on increasing the velocity and artificially lifting the liquids. So we are looking at how do we increase the velocity so that we can be able to push up this liquid that is within the walls of our pipe more effectively. So areas of improvement in management of liquid loaded gas well include: one, well bore heating to prevent liquid loading. When we heat the well bore to the reservoir with the aid of heater cable systems, this will help us to have lesser liquid portion to grapple with. So that's one area that needs to be given attention in terms of application. Then this could also lead to the liquid phase being managed better. Then the next one is insert of tubing joint. With our ability to insert or place tubing joints properly and properly sized tubing joints as well would help us also to be able to manage this liquid loading in gas wells better. So can we go to the next slide? So still on areas of improvement, we have the issue of tubing wall modification. We're able to modify our tubing walls better, especially in terms of sizing. This could help us optimize the gas velocity and, of course, prevent reversal of the liquid phase into the wellbore. So the film flow reversal and droplet flow reversal causes liquid loading. We don't want flow reversal. We don't want this liquid phase coming back into the wellbore. So if we're able to optimize our design of our tubing wall thickness, the diameter, the appropriate diameter, probably depending on the expected reservoir pressure and flowing tubing head pressure as well. Then we also need to be able to modify the properties of the tubing inner wall. We can modify the properties in terms of maybe heat retention and all that. That could help to us to minimize the liquid portion that we will need to deal with. Then another modification that could be explored is application of hydrophobic or hydrophilic coating system with change in wettability. So these forms of coating system could help the liquid film to either easily coalesce together or disperse. So it's important that we explore the ones that can rather help the liquid phase to coalesce together better. Then applying tubing taper, then applying tubing orifice insert. These are also key things that we could explore. Next slide. Yeah. Thank you very much. So that brings our presentation to a wrap. And thank you for your attention. I will hand over to Eras to help us in coordinating the questions. As well, if there are comments from our group mates, our colleagues are here that were part of this presentation. If there are some comments, Obong, I believe you're still around. Mike, if there are comments, please. I think there could be some few minutes for that as well before Eras will lead us on in question. Thank you very much.
Good evening, everyone.
Good evening, sir.
Yeah.
Good evening.
Yeah, I just want to also say something very critical concerning liquid loading in gas wells. One thing we need to understand about this concept is that when liquids flow, irrespective of the source, whether from structures, flow behind pipe, directly from aquifers, or from condensation, what is actually happening in the well bore is the buildup of the flowing bottom hole pressure. Now, when you look at those pictures where they showed you different columns from 1 to 5, what is actually happening at number 5 is that, when the flowing bottom hole pressure increases in the well bore, over time, what you will see is that it forces the liquid back into the reservoir. Now, because it's forcing the liquid back into the reservoir because the bottom hole flowing pressure is greater than the reservoir pressure, because that is the only way flow from the well bore can be in the direction into the reservoir. So as it continues to flow, as the pressure continues to build in the well bore, the liquid will continue to flow back into the reservoir. But what is happening, if you look at that cycle, the liquid loading cycle, is that as it continues to move the liquid back into the reservoir, the pressure in the reservoir will continue to build as well. So the pressure in the reservoir will continue to build until it gets to a point where it becomes higher than the well bore flowing pressure. At that point, you have another reversal of flow from the reservoir back into that is the process whereby you see number 1 and number 5 looking alike, where all the liquids that have accumulated in the well bore have further lifted back to the surface. That is an important concept. And another thing we also need to understand is that this liquid, like the annular flow being discussed, this liquid can flow in the core as droplets, can also flow as films on the wall. Now, if they are flowing as films on the wall, what happens is that they will trickle down and continue to build. But if they are flowing in the core, of course, the superficial velocity of the gas must be high enough to lift all the liquids. Otherwise, we have direct dropping the position of these liquids in the well bore. And the film thickness on the wall depends on the level of entrainment and deposition. Entrainment into the core and deposition on the wall. So if you have some kind of equilibrium. Equilibrium is when you have kind of equal deposition and entrainment in the core. What you are going to have is equal film thickness. But in most cases, we're not going to have equal because the movement in the core, the velocity in the core is always higher than the velocity at the wall. So that makes films on the wall easily trickle down and build at the bottom. But you need to be also very careful because as this liquid continues to, this cycle cannot continue forever because reservoir depletion is a key. And if the reservoir pressure is constantly dropping, the consequence is that it will come to a point when the reservoir pressure, no matter what, may not be able to lift any liquid out again. So that way, you can never have a cycle again. You are going to have just one direction flow where the well itself will die. And that is what we try to avoid. Thank you very much. This is my contribution.
Thank you, my pieces, for that great contribution. I think we have a few questions. So, Obong, you help us in coordinating that alongside Eras, right? So I think there's a question. Well, I think there's a question from Frank. So I'll read it out. I know it's for me and for the group. And if anyone can start helping, otherwise I come in at some place as well. So can we apply anti-scaling agents to removing the liquid films on the tubing? Those liquid films, those blue, light blue parts on the tubing. Frank is asking if we can apply anti-scaling agents to remove the liquid film on the tubing. And then the second question from Frank is, can acidizing help to stimulate the well by increasing gas pressure? Is there anyone that can help us out there? Anyone from the group? So can we apply anti-scaling agents? I think this is something that could be given that may need further careful consideration, because scaling it's a different phenomenon. The chemistry around it is a bit different, because here we are trying to basically manage the liquid films within the wall. So I think the chemistry of anti-scaling agents may not be quite suitable for these liquid films. They could lead to more challenging problems, if you ask me. That's my thinking. That's why from the training I was privileged to attend in the Netherlands, I think the whole idea is using foam in the form of foam or coating agents, like in the last slide. They also had a case where the tubings that was in a lab actually was coated with what they call perspex to some portion, and that perspex was able to cause the liquid film to coalesce better and make it easy for the gas core to lift it up. So I think I would rather go the way of this coating agent or using of foams rather than anti-scaling agent. I think for the anti-scaling, there will be need to consider the chemistry of what we want to apply so that it doesn't lead to more problems. Thank you. I don't know if anyone can help us on the second question. Eras, can you help us on that?
Okay, good evening. My name is Daniel. I would like to speak about the effect of acidizing. Yeah. General acidization, the acidization is done in wells where we have skin around the perforations usually. So when we acidize wells, it helps dissolve the skin around the perforations, which tantamount will increase bottom hole pressure and increase our production rates. But usually when acidizing is done, we have usually experienced a lot of water production in the same vein. So I think it's something for gas wells. I don't expect much of scales around perforations, but if we do have them and we acidize, we tend to have high water production from the aquifer into the well, especially the reservoir is depleted. So I don't think acidizing would help in this stress well. Yes, it can increase the bottom hole pressure, but it will as well bring in water. That's my expectation. Thank you.
Do we still have more questions? Stella, are you still around to help us with anything from YouTube channel? Any questions or comments from YouTube channel?
Okay, I have a question, please.
Okay, go ahead.
Most of the methods or solutions you prefer to handling liquefaction in gas wells, are all these methods to be done before the well is completed, or is it something to be done after, maybe when the problem starts, we have to carry out a walkover to implement these solutions?
Okay, if I get back to the slide. I think some of them will be more of things we apply, after, we carry out walkover and then have them implemented. While some, we need to actually have some of the equipment installed ahead. So for instance, the plunger lift one, I think this could actually, there could be provision for this ahead based on the prediction and all that. You have it installed ahead before you start having this problem. Then that of compression, I think maybe RAS will be the best position to throw more light on that based on his practical examples and field case that he has had. So, Eras, I don't know if you're still here. Then that of bean pumping as well, there could be, you could have this installed ahead, just like you will have your subsea pumps installed ahead and not necessarily waiting for the walkover period. Then the EOR method is similar to the way you apply EOR, of course. So I don't know if that answers the question to a reasonable extent.
Yes, it does. The only why I asked was because I know from your presentation, you mentioned we could have water from either condensation from gas or from the reservoir, like the aquifer in the reservoir itself, maybe through water cooling.
Yeah.
So I'm assuming that water cooling usually is something that you may not envisage at the beginning of your production line.
Yeah.
So if you start experiencing this liquid accumulation in your tubings due to water cooling, most of these solutions may come in like after a walkover. That's why I asked. I was not very sure.
Okay.
But that have an issue, you have to install all of this from the beginning.
Yes, I think so. Pretty much most of them. You have to have because as part of your design phase, if there are signs from some initial study, I think it will be wise to have this installed instead of waiting until you start doing any form of walkover and having them installed, because it will also lead to a waste of time.
Yeah. Okay, thank you.
Thank you very much. So I don't know if anyone from the group has a comment before I hand over to Mike to give some form of closing remarks on our behalf and some form of vote of thanks. Is there any extra comments, extra questions? Are we still here?
Okay. Yes, we are. Good evening, all. Good evening, all.
Good evening.
Okay. I'm Ubong.
Good evening.
Yes, good evening, all. I'm Ubong. I'm sorry, I've been having some serious issues with my network here to take those questions.
Okay.
But I don't know if the question Daniel asked has been treated. I could make a little contribution.
Yes.
Yes, just to add.
It has, but if you still have to, yeah, go ahead.
Okay. Just to add to what you said, some of those methods for mitigating liquid loading are actually considered while the well is being completed, such as the tubing string sizing. So some analysis has to be done to look into the best tubing size that can be used for seeing liquid loading. And some others are carried out while the well has already been put on stream, such as compression, which we saw in the case study that was discussed by our team member, Erasmus. We saw that it took about 5 years and the well was flowing properly until it had the issue where the production declined, and then compression method was considered. So some of these methods are actually considered while the well is being completed, while others come on stream as well intervention methods. Thank you.
Okay, thank you.
Good evening, all. Please, I just have a little question.
Yes, go ahead.
It's just a clarification, please. I'm sorry for.
No problem. That's what the session is for.
Okay, the plunger pump we talked about, is it the same thing as artificial lift where you have to use submersive pumps?
Yes, somewhat. It's somewhat that. Very much in tune, very much in line with that.
Okay, what in a case where you did not install all this, so
in your system?
Yes, in your system, and you end up having a low pressure, you experiencing the problem, then maybe you end up not producing. So is there any method that you can use? Like maybe, I don't know if there is any method. Because why I ask this question is there is operation we are on right now. So
okay.
this is like is similar to this scenario. I'm not the engineer that designed the job, but I'm just like imagining maybe this is what we have. So what we are doing currently was actually outside Nigeria, but we are doing something like hydraulic fracturing in the well. Unconventional.
Okay.
We have to fracture the well.
Eras, are you around? Hello. Go ahead anyway. I was trying to see if he's around so he could make some inputs with regards to this, but go ahead, please.
Okay, so my question is this: where you could not install all this and take all these plans, so now you end up not producing what you want. So the well is like dead. So what can you now do to revive it? So as I said, what we are doing here right now was what we call unconventional hydraulic fracturing. So is there any other thing you can do?
I think gas lift, if possible, though it's just that it may take some time to now get it installed in the system since it wasn't part of the initial design. But I think gas lift is something that could be worth considering.
Okay. All right. Thank you so much.
So do we have any other comment with regards to this last question? Because I think it touches very much on the core essence of this session. Any other person with comment on this current problem that our colleague is having in the asset? So I think in the absence of that, Mike, are you still here to help us with vote of thanks?
Yeah.
Any further remarks? Yes, sir.
I'm here.
Please take the floor, is yours.
Thank you very much, Doc. Excellent presentation. On behalf of SPE Section 103 Production and Operation Study Group, I would like to express my sincere appreciation to everyone present in this meeting today, and also special thanks to every member of the study group who has made this event to be a success. It has been a very taxing period for everyone to come up with this study presentation today. And we look forward to a more promising technical subject in our subsequent subject engagement to come. And I wish everyone a pleasant evening. Thank you.
Thank you very much.
Thank you.
I think we are left with closing prayer. So can someone from the audience just close us? Can someone from the audience close us?
In the name of the Father, and of the Son, and of the Holy Spirit. Amen. Heavenly Father, we thank you for this wonderful presentation. We thank you also for our presenter. We thank you for the SPE, Port Harcourt branch. We thank you for all you have done for today for us. We thank you for leading us all through the pandemics. We thank you for your protection, safety otherwise, in our workplace, at our home. We worship you. We say, hallowed be thy holy name in Jesus' name. As we are about to go, oh God, we are not leaving your presence. May you be with us, go with us. Some of us that are still in our office, be with us as we go home. Protect us from the evil ones. May we go freely, and may we go and may continue to cover us with the blood of Jesus. Stay with us and always be with us from now, forevermore. Amen.
Amen.